So when we want derivatives of the vector function, a vector function, let's think back. Let's go all the way back to definition here of derivative. So I've got the derivative of vector r, vector function r, vector r here. Okay. So, you know, you can use the same notation. You can use the DDT Leibniz notation. Prefer probably just use the r prime notation. So it's all the same. Like I said, we can even take this back to the definition, and it'd be the limit as h approaches 0 of r t plus h minus r t divided by h. Remember that? Way back, way back. So, very definition, very same. So, hopefully then you're thinking it's going to mean basically the same thing. This was, the way we got that was with just regular functions. That was secant line slopes, right? And this gave us the slope of the tangent line, or the counterpart for functions. That was the slope of the tangent line. Well, good news, okay? R prime of t, it's going to be the tangent vector defined by of the curve that's defined by the r vector function. It's the tangent vector. And it's okay. So kind of in a three-dimensional general view of it here. Okay, so let's say we got this space curve, whatever it looks like, in and out wherever it goes. Well, if I come out here at t, define r prime there. R prime is that tangent vector at that particular value of t. Wherever that point is at t, yeah, r is going to be that tangent. R prime is going to be that tangent vector. So, yeah, it's good. It's good news. So it's a tangent. So remember, there would be a tangent line there. R prime is the vector parallel to that tangent line. So that's what R prime is. Also good news is that if I've got R of t is f of t, g of t, h of t. One drawback of all this is got all those parts, so it can get lengthy to write, but r prime of t, good news is, what you hope is the way this would work, is you just do the derivatives of each individual part. So r prime is going to be f prime of t, g prime of t, h prime of t. Pretty sweet, huh? Pretty nice. So yeah, that's going to give you that vector. Now, a lot of times they like these unit vectors. Same thing on these. So we'll call it the unit tangent vector. So we're going to, and that's just like we did before. We're just going to unitize it, meaning make it a 1 unit long vector. And so remember the way we did that. So they call it t, the t vector, big capital T vector there. And remember how we unitize it, we would take that vector and divide it by its magnitude. That makes it a unit long, as far as lengthwise magnitude is. So it's r prime of t, and then just divide that by its magnitude. So it has the same direction as r prime. It's just that it's 1 unit long. Standardizes the length, I guess, is one other way to think of it. Okay? So that's, well, I guess you can get some complicated derivatives, but it's not too bad. All right, so for RT equals 1 plus t cubed t e to the minus t sine of 2t. It's our vector function. A, let's find r prime of t. Well, easy enough. We know about derivatives, so here's our chance to bring out our skills, I guess. 3t squared is the derivative there. All right, so still have to remember the old rules. Product rule comes up here. Derivative of the first times the second, and then rotate that, so it would be plus t times the derivative of e to the minus t, which would be e to the minus t times the minus 1 because of the chain rule. All right? It's been a while. And then we have sine of 2t, which is also a little chain rule there. Sine, the outside sine, so the derivative of that's cosine, but you do the derivative of the inside, so it's that. I guess we can clean it up, can we? But yeah, pretty much it. 3t squared, e to the minus t, t minus t minus t, and then 2 cosine 2t. Okay. All right, so B, let's do this. How about find the unit tangent vector. At t equals 0. Yeah, so usually what we want is just a specific, we could do it general, I guess, but we want a specific t value here. The unit tangent vector is a specific value. So t, so this unit tangent vector be t, the t vector at 0. So that's just going to be r of 0 divided by the magnitude of r, r prime of 0, divided by the magnitude of r prime 0. Well, r prime 0 is nice. It's what, 0, 1 minus 0, so it'd be 1. And then 2 times cosine of 0, so that's 2. Right? With me there? All right? Do that, 0, 1, 2. And then divide that by the magnitude. Well, the magnitude is easy. You just do the square root of the squares there. So we could say it's 0, 1, 2 divided by square root of 5, which, I don't know, they may go ahead and put that square root of 5 in there, so it'd be 0 divided by square root of 5, 1 divided by the square root of 5, and 2 divided by the square root of 5. Get down to it there. I mean, yeah, that's probably, well, and then they would probably rationalize the denominator, but you can if you want to there. Yeah, not too bad, right? Just have to remember some of the old rules there. All right. Now let's kind of take this kind of step beyond here, that kind of like us to make sure we know what we're finding a little bit, what this means. All right, so let's say we've got R of t equals t squared I vector plus t cubed j vector. So I've bumped it down. Now we're just doing the two-dimensional vector function. All right, so sketch the curve with vector function r here. So again, all that means is, yeah, I mean, this technically is it's just a series of vectors, moving vectors or growing vectors, or, yeah. Moving is probably a better word because sometimes they shrink, I guess, but this would be growing. Anyway, the curve is just the parametric, associated curve of the parametric equation. So the curve here is just going to be x equals t squared, y equals t cubed, whatever curve that curve looks like. So that's the curve they're talking about. So notice, yeah, this is just an x, wow, xy curve, two-dimensional curve. 0, 0. T equals 1, we'd be at what? 1, 1, 1. T equals 2, we'd be at 4, 8. And I think it's going to jump quite a bit because the next one would be T equals 3, I'd be at 9. The next one, t equals 3, if I did integers 9, 27, so yeah, so it's going to jump out there, so something like that. Extend a little bit. And then notice there's not another side to that, because if I went t equals negative 1, look at that one. What do you got there? Well, 1, negative 1, I guess you do that other side. 1, negative 1. All right, so it would be 1 and negative 1. So it does, okay, so it does do that. That's kind of another side to it. Anyway, because I think, yeah, 2 would be a 4 negative, or yeah, 4 negative. My bad. Forget what I said before. All right, so it looks like that. It comes back in at 0, so it kind of has a little bit of a corner there. Anyway, all right, so that's the curve. That's the curve. All right, what's r prime? The derivative. Oh, easy enough. If we, I guess, probably our rule of thumb here is if they give us it in ij component form, let's give the answer in ij component form. So it'd be 2ti plus 3t squared j, just the derivative there of each. Okay, now, third one here. How about, let's find r prime of 2 and sketch it, and, oh wait, that's not what I want. All right, so let's find r of 2, let's do it this way, and r prime of 2. Let's find those two. So R of 2, that's just the vector function evaluated at 2, so that would be 4i, so we did that, 4i plus 8j. And then R prime of 2 is 4i 3 times 4, 12j. Is that right? Yeah, 12j. All right, so those two things, yeah, those two things are just vectors. And so D part here, the other part is wants to do. Let's sketch R of 2 and R prime of 2 on this same thing here. It's fairly easy, especially if I pick a point you've already graphed. So R of 2, that's just going to be your position vector when t is 2. And so R of 2, well, it's this vector, which is the I component's 4, the horizontal, and then the vertical component's 8. But if you think about it, R of 2 is just going to be this, isn't it? R of 2 would be the best. I mean, we could put it anywhere, but it's just that vector that connects the origin to that. That'll be the terminal points at 4. Now, R prime of 2, well, this is what R prime of 2 is. It's 4i plus 12j. And so that's horizontal 4. But to put it in the appropriate spot, what is R prime? Well, it's that tangent vector. We didn't make it a unit vector like here, but it's just that tangent vector at that particular point. So best place to put it would be here. So I'd go, what, 4 this way. I have 4, so it'd be out of 8. And then 12 this way. It's estimated here, okay. Maybe because it is going to be tangent here. Maybe I should have done it in a different, on a different axes, but anyway, so that's what you're finding as far as the derivative is concerned. It is going to be tangent, so it should be. Again, I probably should make it a little higher so it'll be more tangential there, but you get the idea. All right. What you Okay, and so here's the next one. Talk about this. Here's another thing they'll have us look at. Find parametric equations for the tangent line to the curve at point 3, 2, 1. This is the curve. X equals 3t squared, y equals 2t, z equals t cubed. So what we've done so far is we haven't talked about, all right, so this is a space curve. We haven't talked about the tangent line to a space curve, but under the vector function umbrella, if you will. So if I think about this as a vector function, 3t squared, 2t, t cubed, then I know the tangent line is made up, or I can get the tangent line off of that, or a specific tangent line by using the vector derivative, right? So r prime of t at a specific t value, that'll give me my tangent curve, tangent line, or tangent vector, is the best way to put it. And that's easy enough then to think of, so that's 6t to 3t squared, right? The little catch on this one is, all right, so I want the parametric equations for the tangent line to the curve at point 321. What do I need here to figure that out, though? I need t, don't I? And I've been given, what are these? All I'm given here is the x, y, z. So I got to figure out what t is to give me that x, y, z. Now, yeah, so if I look at, so again, those go along with this. You have to be careful, right? Because, well, if I can do it technically, I guess, with any of these, but here's the thing. If I use the fact, well, x is 3, and I know that x is 3t squared, that gives me either t is 1, so x is 3t squared, but I also know that x is 3. So that would tell me 3t squared equals 3. Well, the deal on that is, figure that out, that's t equals 1, t equals positive or negative 1. The only problem with that is, that may not work in the others, right? So it might be best to look at, if you got some simpler equations, you may want to go with that. Like here, I would have the y value is 2, so 2t equals 2. That, there's only one way, one solution to that. So that's what I'm saying. We probably want to use the y equations here. So be careful on that. The x, you could say, well, it could be 1 or negative 1. So there, you might be thinking, well, there might be 2 tangent lines here. Sometimes they might trick you like that, but I don't think it will. They could. But since the y is 2 and y is 2t, there's only one solution here. The t has to be 1. So my tangent line is going to come when t is 1. So this will give me the tangent vector. So my tangent vector at t equals 1 is r prime of 1, which is 6, 2, 3. But the instructions were, I want the parametric equations for the tangent line. So that just gives me a tangent vector. The line is, of course, associated with that. So how would I get the line? Well, on a line, remember, what you need is you need a vector, which is the direction, and then you need a point for a line, right? To get, like to make the analogy here, I've got this vector, so that gives me the direction. The tangent line, I would still, if I wanted to get the tangent line, I would still need some more information there. I need a point along with that vector. Well, in this case, I've got the vector. I just need a point on the line. Well, it just so happens I have a nice handy point available, don't I? Because if we're going to be tangent to this, or this curve, at this point, that's going to be a point on the line, right? So 3, 2, 1 is our point. It's a point on the line. That's our vector. And then the point on the line is 3, 2, 1. And so then remember how you put that together. The x equals, you do your point, your x value, plus then your x component times t, x component of the vector, right? And then the y, do the same things. Do the y value plus then the vector component, y component there. And then z, the z part of the line would be 1 plus 3t. Good? Make sense? Good with that? Okay.